Newtonian mechanics is one of the most fascinating and fundamental parts of physics, and it's something we all experience every single day. Whether you're walking to school, riding a bike, or just tossing a ball with a friend, Newton's ideas are quietly at work behind the scenes, governing how things move and interact. Let's start from the very beginning and talk about everything you need to know in a super chill, real-world way without any fancy math symbols. So first off, who was this Newton guy? Isaac Newton was a pretty brilliant dude from the 1600s. He wasn't just into apples falling from trees, he was into understanding why things moved the way they did. When he thought about stuff falling or moving, he wasn't content to just say, well, that's how it is. He wanted to figure out the rules that made the universe tick. And guess what? He did. He came up with 3 basic laws that explain almost all the motion we see in everyday life. Let's go through them one by one with loads of examples. The first law is all about something called inertia. That's just a fancy word for saying that if something is sitting still, it'll keep sitting still, and if it's moving, it'll keep moving unless something messes with it. Picture this, you're chilling on your skateboard. You're not moving, just standing there. Unless someone pushes you or you kick off the ground, you're going to stay exactly where you are. That's inertia. Now, once you do push off and start rolling, you won't just stop on your own. If there was no friction or air resistance, you'd keep going forever. But in real life, the wheels slow down, the ground isn't perfectly smooth, and eventually you stop. Still, the idea is that without some outside force acting on you, your motion wouldn't change. Another fun example? Think about when you're riding in a car and it suddenly stops. Your body lurches forward. That's because your body was moving with the car, and when the car stopped, you still wanted to keep going. That's your body's inertia. That's why we wear seatbelts, to stop that inertia from making us fly through the windshield. So yeah, even your seatbelt is part of Newtonian mechanics. Now let's talk about the second law. This one is about how much stuff is moving and how hard it is to change that motion. Imagine you're pushing 2 grocery carts. One is empty and the other is loaded up with soda bottles. You push both with the same strength. The empty one zooms forward easily, but the heavy one barely moves. That's because it takes more force to move heavier things. This law is really about how force and motion go together. The more force you apply, the more the object speeds up. And the heavier the object is, the more force you need to make it speed up the same amount. Another classic example? Kicking a ball. Kick a soccer ball and it goes flying. Try kicking a bowling ball the same way and you might just hurt your foot. That's because the soccer ball has less mass and it doesn't take as much force to get it moving. It's pretty intuitive stuff once you think about it. And here comes the third law, which might be the coolest one. Every action has an equal and opposite reaction. This law is everywhere. You push something and it pushes back on you. That sounds weird at first, but think about when you jump off a small boat onto a dock. As you leap forward, the boat slides backward. You pushed on the boat and the boat pushed back on you. Or think about walking. Your foot pushes back on the ground and the ground pushes you forward. You don't even notice it, but it's happening with every step you take. Birds flying? They push the air down with their wings and the air pushes them up. Rockets launching? Same thing, they shoot gas down and that gas pushes them up into space. It's wild how this one law explains so many things. Let's not forget about friction, which is the resistance you feel when 2 things rub together. Friction is why your shoes grip the ground and you don't slide around like you're on ice. It's also why you stop skating eventually. Friction between the wheels and the ground slows you down. Without friction, life would be like one of those cartoons where everyone's slipping and sliding all over the place. Another key part of Newtonian mechanics is gravity. You don't need a fancy explanation for gravity. Drop something, it falls. But Newton took it a step further. He realized that every object pulls on every other object. That's why apples fall from trees and why the moon stays in orbit around the Earth. Gravity isn't just about stuff falling, it's the force that keeps planets, stars, and galaxies together. And here's the crazy part, it works over huge distances. The sun pulls on the Earth from millions of miles away. You pull on the Earth and the Earth pulls on you. That's why you stay on the ground. Now, let's look at real-life situations where Newtonian mechanics shows up. Say you're playing basketball. You dribble the ball and it comes back up to your hand. Why? Because you're applying a force to it and gravity brings it back down and then the ground pushes it back up. That's Newton's third law again. The floor pushes the ball upward as the ball hits it. And as you shoot the ball toward the hoop, you're calculating, even if you don't realize it, how fast to throw it, at what angle, and how much force to use. All of that is Newtonian physics happening in your brain in real time. Think about riding a bicycle. When you pedal, you're applying force to the pedals, which turns the wheels. The more force you use, the faster you go. Again, Newton's second law. And when you hit the brakes, friction slows the bike down. If you let go of the handlebars and coast down a hill, that's inertia. You're moving, and unless something like air resistance or the brakes stops you, you'll keep moving. Even just standing still is full of physics. You're applying force downward due to your weight, and the ground is pushing back with equal force to keep you from sinking. Your muscles are working constantly to balance and counteract little forces that try to move you. That balance is Newtonian mechanics in action. Ever tried pulling a sled? If it's empty, it's easy. If it's full of snow or carrying your little cousin, it takes more effort. You're applying force to overcome inertia and friction. And if the sled's moving already, it's easier to keep it going than to get it started from a stop. That's Newton's laws again. Motion wants to stay in motion, but starting something takes force. Newtonian mechanics also explains car crashes. When two cars crash, the forces involved depend on their mass and how fast they were going. The impact is shared between the two, and the consequences depend on how strong the cars are, what direction the impact came from, and how well the passengers were restrained. Crumple zones in cars are designed using Newton's ideas. They absorb force over time so that the passengers feel less of it. Let's say you're throwing a frisbee. As you throw, you're applying force in a direction, and the frisbee moves in that direction. But it doesn't go forever. Gravity pulls it down, and air resistance slows it. If you throw it into the wind, you have to adjust your angle and force. All of this is Newtonian thinking, whether you realize it or not. Playing pool. Every shot you take is an experiment in Newtonian mechanics. You hit the cue ball, it hits another ball, they both move. The way they bounce off each other, the speed, the direction, all of that can be explained by Newton's laws. Even dancing involves physics. When you jump, spin, or land, your body is interacting with the floor. You're applying forces, and the floor is pushing back. The timing, the control, the balance, all of it relies on understanding, even intuitively, how motion works. If you're into video games, even those rely on Newtonian mechanics to make them feel realistic. When characters jump, slide, or crash into walls, game developers use the same physics rules to make those movements look believable. That's what makes Newtonian mechanics so powerful. It doesn't just explain obscure science experiments, it explains everything. How planes fly, how cars drive, how athletes perform, how machines operate. It's the physics of the everyday world, and the best part? You don't have to be a physicist to appreciate it. You've been living with these laws your whole life. You already understand them, even if you didn't know the names. Whether you're sliding across a hardwood floor in socks, pulling your dog on a leash, or jumping into a swimming pool, you're living proof that Newton was right. So next time you're out and about, take a second to look around. Think about how things move, how they stop, how they interact. It's not just motion, it's a beautifully choreographed dance governed by laws that have stood for centuries. Newton's laws aren't just old science, they're the script behind every motion we see. And now that you see it too, the world might feel just a little more magical. Electrodynamics and electromagnetism might sound like something out of a superhero movie, but honestly, they're just describing how electricity and magnetism are connected. And the cool part? This invisible connection runs our entire modern world, from the moment you flip on your bedroom light to the second you scroll through your phone or microwave your food. It's not magic, it's just physics doing its thing. So let's break it down in a way that actually makes sense, using everyday life and no complex math symbols or weird jargon. Let's start with electricity. You've probably heard of electric current, right? That's just a flow of tiny particles called electrons. They move through wires and circuits kind of like water flows through pipes. Flip on a light switch and bam, the circuit is complete and electrons start moving. Those moving electrons are what power the light bulb, making it shine. Same with your phone charger, your fan, your computer, anything electric. Now, magnetism might seem like a totally different thing at first. You've probably played with magnets as a kid, maybe you've felt the invisible force that pulls them together or pushes them apart. But what's really going on there is also about electrons. In magnets, the electrons inside the material are spinning and moving in a way that creates a magnetic field. It's invisible, but it's powerful. Here's where things start to get wild. Electricity and magnetism aren't separate things. They're two sides of the same coin. Moving electricity creates magnetism, and changing magnetism creates electricity. That's the heart of electromagnetism. So if you've ever seen those huge wind turbines or even a simple bicycle dynamo that powers a light as the wheel spins, you've seen electromagnetism in action. Spinning magnets inside coils of wire can generate electricity. And running electricity through coils can create magnetic fields. That's how motors and generators work. Let's bring it down to something super relatable. Think about your phone's charging cable. Inside, there's a wire carrying electric current. That current creates a magnetic field around the wire. It's tiny, but it's there. Now imagine wrapping that wire into a coil. That field gets stronger and more focused. And if you place a piece of iron inside that coil, boom, you've got an electromagnet. This kind of thing is used in everything from doorbells to MRI machines to maglev trains. Remember those wireless phone chargers? They work on this exact principle. The charger has a coil that creates a magnetic field when current flows through it. Your phone has a coil too. When you place your phone on the charger, the magnetic field from the charger induces current in your phone's coil. That current charges your phone, no wires needed. Just electromagnetic induction doing its thing. Electric motors are another everyday application. Ever used a fan, a blender, or an electric scooter? All of these use motors that rely on electromagnetism. Inside, current flows through coils, creating a magnetic field. That field interacts with magnets to spin something. That spinning motion is then used to move air, mix a smoothie, or drive your wheels, and let's not forget speakers and microphones. Your earbuds? They've got tiny coils and magnets that convert electrical signals into sound waves. Microphones do the reverse. Sound waves move a diaphragm that changes a magnetic field, creating an electric signal. Every time you record a voice memo or talk to your friends on a call, you're using electromagnetism. How about transformers? Not the robots, though those are cool too, but the devices on power poles or inside your charger blocks. They're used to increase or decrease voltage. This happens by passing alternating current through coils of wire, which creates a changing magnetic field. That field then induces a voltage in another coil. Depending on how many loops each coil has, the voltage goes up or down. That's why the power that reaches your home from power stations is stepped down to safe levels. Let's go even deeper into real life. Ever wondered how your car's engine starts when you turn the key or push a button? That's an electromagnet pulling a switch called a solenoid, which lets current flow to the starter motor. And when the engine's running, the alternator generates electricity to power the car and recharge the battery, again, through spinning magnets and coils, credit cards, and metro passes. Yup, electromagnetism. The strip on the back stores information using tiny magnetic regions. Machines read that info by detecting how those magnetic fields change. It's fast, efficient, and all thanks to how electrons and magnets play together. Let's switch gears a little and talk about static electricity. Ever felt a shock when you touched a metal doorknob after walking on a carpet? That's a mini electrodynamics moment. Rubbing your socks on the carpet builds up an imbalance of electric charge. When you touch the metal, that charge jumps across as a tiny spark. It's the same basic idea as lightning, just on a much smaller and safer scale. And speaking of lightning, that's one of the most dramatic examples of electrodynamics in nature. Thunderclouds build up massive amounts of electric charge. When the difference between the cloud and the ground gets big enough, electricity discharges as lightning. That's a crazy amount of current moving through the air, and it creates both light and sound. Even the Earth itself has a magnetic field, like a giant bar magnet. It protects us from solar radiation and helps birds migrate. And the reason we have this magnetic field? It's believed to come from molten iron moving inside Earth's core, generating a magnetic field through motion, just like a dynamo. There's also electromagnetic waves, which include visible light, radio waves, microwaves, X-rays, and more. All of these are made by vibrating electric and magnetic fields. Your Wi-Fi, your Bluetooth headphones, your TV remote, they all send and receive electromagnetic waves. Even the light from the sun? Electromagnetism. That's right, the very sunlight that warms your face and makes life possible is part of the electromagnetic spectrum. So, from the moment you open your eyes in the morning and check your phone to the second you turn off the lights and crash into bed, electromagnetism is everywhere. It's the invisible lifeline of our entire world. Every gadget, every signal, every sound you hear through headphones or video you stream, it's all powered by the magical, mind-blowing dance of electrons and magnetic fields. Once you start noticing it, you'll see it's impossible to escape. And honestly, why would you want to? Understanding how electricity and magnetism work together not only makes you smarter, it helps you appreciate the science that powers your life. It's not just theory, it's real, practical, and honestly pretty amazing. Relativity is one of those topics that sounds super complicated at first, but once you get the hang of it, it's honestly one of the coolest things in all of physics. It flips the way we think about space and time, actual space and time, on its head. When most people hear the word relativity, they picture a white-haired Einstein scribbling equations on a chalkboard. But the idea itself? It's not just for geniuses or science nerds. It's about understanding how the universe behaves when things get really fast, really massive, or both. And it actually connects with real life in ways that might surprise you. Let's start with the basics. There are two kinds of relativity: special relativity and general relativity. We'll focus more on special relativity for now because that's where the wild stuff begins. Special relativity deals with things moving at constant speeds, especially speeds close to that of light. The main idea? The laws of physics are the same for everyone, no matter how fast they're moving, as long as they're not accelerating. And this one's a big deal: the speed of light is the same for everyone, no matter what. That second idea might sound weird at first. Like, if you're on a train and throw a ball forward, someone standing on the platform sees the ball moving faster than you do, right? But with light, it doesn't work like that. If you shine a flashlight on a moving train, someone on the train and someone on the platform will both measure the light moving at the exact same speed. That's mind-blowing, and it messes with our idea of time and space, because if light speed doesn't change, something else has to give. And what gives? Time and space. This leads to two major consequences of special relativity: time dilation and length contraction. Let's tackle time dilation first. Imagine you're on a spaceship flying near the speed of light. To someone watching you from Earth, your clock is ticking slower than theirs. That's not a trick or a malfunction, it's just how time behaves at high speeds. For you inside the ship, everything feels normal. But back on Earth, time is passing faster. This is real. We've actually observed it with extremely precise clocks on fast-moving jets and satellites. It's not science fiction. Then there's length contraction. When something moves really fast, it appears shorter in the direction it's moving. So, if you're zooming past Earth in a spaceship, someone watching from Earth would measure your spaceship as being shorter than it is when it's at rest. Again, from your perspective on the ship, everything feels fine. But for an outside observer, space itself is different. Now let's bring this into everyday life. GPS is one of the best real-world examples of relativity at work. Your phone's navigation system uses signals from satellites orbiting Earth. These satellites are moving pretty fast, and they're also farther from Earth's gravity, which brings general relativity into the picture too. But for now, just focus on the speed. Because of special relativity, the atomic clocks on the satellites tick at a different rate than clocks on Earth. If engineers didn't account for this, your GPS location would be off by kilometers. Every single day. So yeah, relativity literally helps you find your way to the nearest pizza place. Now let's touch a bit on general relativity just to complete the picture. General relativity adds acceleration and gravity into the mix. It tells us that gravity isn't just a force between two objects, it's actually the way massive objects warp the space and time around them. Picture a trampoline with a bowling ball in the middle. If you roll a smaller ball nearby, it curves around the dip created by the bowling ball. That's kind of how gravity works in general relativity. This idea explains why planets orbit the sun, why light bends around stars, and even why time passes differently near massive objects. Astronauts on the International Space Station age just a tiny bit slower than people on Earth. And near a black hole, this effect becomes extreme. Time almost stands still compared to Earth. That's not just cool, it's essential to understanding how the universe works. But let's bring this back to you. Ever watched a science fiction movie where someone travels near the speed of light and comes back to find everyone else has aged more than them? That's based on real physics. It's called the twin paradox. If one twin goes on a super-fast space journey and the other stays on Earth, the traveling twin will be younger when they reunite. Not by magic. Not by a trick. Just because time itself ran differently. And what about the idea that nothing can go faster than light? That's also part of special relativity. The faster you go, the more energy you need to keep accelerating. As you get closer to the speed of light, your energy requirements shoot up like crazy. Eventually, you'd need infinite energy to hit light speed, which just isn't possible. That's why we can't build a spaceship that breaks this cosmic speed limit. It's like trying to run faster than your own shadow. Another mind-bending idea is that mass and energy are really the same thing. You've probably heard the famous phrase, mass equals energy times something. That means a tiny bit of mass can be turned into a huge amount of energy. This is what powers nuclear reactors and atomic bombs. It's also how the sun shines. Inside the sun, tiny particles smash together and some of their mass turns into light and heat. That's energy born from mass, and here's something else. Relativity isn't just some deep space, high-speed spaceship kind of thing. It affects every part of our reality. High-energy particles from space, called cosmic rays, hit Earth's atmosphere all the time. Some of them travel so fast that if relativity didn't slow down their internal clocks, they'd never make it to the ground before decaying. But because of time dilation, they do. Relativity lets them survive long enough to be detected by instruments here on Earth. The more you learn about relativity, the more you realize just how flexible and strange our universe is. Space and time aren't fixed. They're part of the same fabric, and they bend and stretch depending on speed and gravity. Once, people thought space was like an empty stage where things happened. But now we know the stage is part of the play. It shifts and twists as the actors move. Even though this all sounds super sci-fi, it's grounded in experiments and observations. We've tested relativity over and over, and it always checks out. Particle accelerators, satellites, lasers, and atomic clocks have all confirmed its predictions. It's not just a theory, it's the way the universe actually works, and the craziest part? This all started because Einstein decided to question something as simple as the speed of light. He asked, what if it never changes, no matter how you move? That one question cracked open an entirely new way of looking at reality. A way that lets us understand black holes, GPS, the expansion of the universe, and so much more. So yeah, relativity might seem complicated at first, but it's really about one simple truth: the universe isn't what it seems. Time can stretch. Space can bend. And everything you thought was fixed might just depend on where you're standing and how fast you're moving. That's not just cool, it's revolutionary. And once you see the world through that lens, nothing ever looks the same again. Nuclear and particle physics might sound like something only scientists working in underground labs care about, but the truth is, this stuff connects directly to our lives in powerful and sometimes surprising ways. It's all about understanding what the universe is made of at its deepest level, and how the tiniest particles hold the biggest secrets. Let's start with nuclear physics. That's basically the study of the nucleus, the tiny center of an atom. Inside that nucleus are protons and neutrons, packed together by something called the strong nuclear force. This force is crazy powerful. It's what keeps the nucleus from flying apart, because all those protons are positively charged and would normally repel each other like mad. The strong force overpowers that repulsion and holds everything together. It's like the glue of the universe. Now here's where it gets interesting. Sometimes nuclei aren't stable. They can break apart or change into something else. That process is what we call radioactivity. There are a few different kinds like alpha, beta, and gamma decay, and each one involves the nucleus doing a kind of internal reshuffling. When that happens, energy gets released, and that energy can be useful, dangerous, or both. For example, nuclear power plants use a process called nuclear fission. That's when a heavy nucleus like uranium splits into two smaller nuclei, releasing a ton of energy in the process. This energy gets turned into electricity. Nuclear power is one of the most efficient sources we have, but it comes with challenges like radioactive waste and safety concerns. Think Chernobyl or Fukushima. Those disasters weren't just scientific failures, they were reminders of how powerful and risky nuclear energy can be. On the other hand, there's nuclear fusion, which is kind of the holy grail of clean energy. Instead of splitting atoms, fusion joins them together. It's what powers the sun and every star in the sky. Two hydrogen atoms fuse to make helium, and in doing so, they release a massive amount of energy. If we could get fusion to work reliably on Earth, it would be a game changer, basically limitless energy with almost no waste. Scientists are working on it, with giant machines like tokamaks trying to replicate the sun's core right here on Earth. We're not quite there yet, but we're getting closer. Now let's zoom in even more, to particle physics. This is where things go quantum. Particle physics isn't just about atoms or even nuclei, it's about the fundamental building blocks of everything. We're talking quarks, leptons, bosons, and more. These are the tiniest known things in the universe, and they interact in mind-bending ways. The most famous model that describes all of this is called the Standard Model. It's like a periodic table for particles. In it, we've got quarks, which make up protons and neutrons. We've got leptons, like the electron. And then we've got force-carrying particles. These are the messengers of the universe. The photon carries electromagnetic force, the gluon carries the strong force, the W and Z bosons carry the weak force, and the graviton, well, we haven't found that one yet, but it would explain gravity if it exists. One of the coolest discoveries in recent times was the Higgs boson. For decades, scientists suspected there was a field that gave particles mass, like an invisible molasses that slows particles down and gives them weight. That field is the Higgs field, and the Higgs boson is the proof that it exists. We finally found it in 2012 at CERN's Large Hadron Collider. That was a huge moment in physics. Speaking of CERN, that place is wild. It's basically a giant particle accelerator buried under the border of France and Switzerland. It accelerates particles to near light speed and smashes them together to see what pops out. It's like a giant microscope for the smallest parts of the universe. And every time we do one of these collisions, we learn more about how the universe came to be. Now, why should you care about any of this? Well, for one, this kind of research leads to real-world technology. Particle accelerators have been used in medicine for cancer treatments. PET scans, which help diagnose diseases, rely on nuclear physics. Even your smoke detector uses a tiny bit of radioactive material to do its job. And let's not forget nuclear medicine, using radioactive isotopes to track and treat diseases inside the body. Then there's the big picture. Particle physics helps us answer questions like, what is everything made of? Why does anything have mass? Why is there more matter than antimatter in the universe? These questions sound philosophical, but they're rooted in real data and real experiments. Understanding particles helps us get closer to understanding the beginning of the universe. How everything started from a tiny, hot, dense point and expanded into the cosmos we see today. There's also the mystery of dark matter and dark energy. We know they're out there. Dark matter holds galaxies together, and dark energy is causing the universe to expand faster and faster. But we don't know exactly what they are. Some scientists think they might be related to undiscovered particles that go beyond the standard model. That's why we keep building bigger and better detectors to find out what's lurking in the dark. And then there's antimatter. It's like regular matter but with opposite charge. When a particle and its antiparticle meet, they annihilate in a flash of energy. This is a real thing, not just science fiction. We can even make antimatter in labs, though just in tiny amounts. The big mystery is why there's so much more matter than antimatter in the universe. If the Big Bang created both equally, where did all the antimatter go? Solving that could change our entire understanding of reality. In the end, nuclear and particle physics are all about diving deeper into the structure of reality. It's about peeling back the layers to see what's underneath. And even though the particles are tiny, the questions are huge. We're talking about the origin of the universe, the fate of stars, the nature of time and space, and even the future of energy on Earth. Whether it's building nuclear power plants, creating advanced medical tools, or unlocking the secrets of the cosmos, this field touches every part of our lives. And who knows, maybe one day understanding these particles will help us solve climate change, travel to other planets, or even manipulate matter itself in ways we can't yet imagine. So yeah, nuclear and particle physics might start small, but their impact is anything but. They give us a glimpse into the workings of the universe, from the tiniest particles to the biggest questions. And in that search, we find not just answers, but the future. Astrophysics and cosmology aren't just about stars and galaxies and big scary words. They're about understanding where we came from, what's out there, and where we're going. It's the story of the entire universe, and somehow our tiny little lives are connected to it. Whether you're looking up at the night sky and wondering what those points of light are, or you're deep diving into what makes up space-time itself, you're doing cosmology. And trust me, once you start, it's hard to stop. So let's start from the very beginning. Like the very beginning. The Big Bang. The Big Bang wasn't an explosion in space, it was an expansion of space. A tiny point, unimaginably hot and dense, expanded rapidly, and it hasn't stopped expanding since. That point wasn't sitting in a blank void waiting to explode, it was everything. Space, time, matter, energy, it all began there. There was no before the Big Bang because time itself started with it. That's mind-bending, I know. In the first moments after the Big Bang, the universe was just a hot soup of particles. No stars, no galaxies, just fundamental particles bouncing around like crazy. As things cooled down, particles combined to form atoms, mostly hydrogen and helium. Then gravity stepped in. It started pulling things together, forming the first stars and galaxies. Those stars burned, fused atoms into heavier elements, and exploded in supernovae, spreading those elements across the cosmos. Every element in your body, carbon, oxygen, iron, was made in a star. So, yeah, you're literally made of stardust. Now, this is where astrophysics kicks in. Astrophysics is like the engine room of cosmology. It's the physics of space, how stars work, how galaxies form, how black holes behave, all that jazz. It's about the forces and particles that make the cosmos tick. It asks questions like, why do stars shine? What happens when they die? Why do galaxies spin the way they do? How do black holes bend space and time? Speaking of black holes, let's talk about them. Black holes are what happens when gravity wins. When a really massive star runs out of fuel, it collapses under its own gravity. If it's massive enough, nothing can stop the collapse, not even the pressure from atomic nuclei. The core shrinks down to a point of infinite density called a singularity. Around that singularity is the event horizon, the point of no return. If you fall past it, you're not coming back. Not even light can escape, but black holes aren't just vacuum cleaners sucking up everything around them. They actually play a huge role in shaping galaxies. Supermassive black holes, millions or even billions of times more massive than our Sun, sit at the centers of most galaxies, including ours. They're like galactic anchors influencing how stars move and how galaxies grow, and get this, black holes aren't completely black. Thanks to Stephen Hawking, we know they can actually emit radiation. It's called Hawking radiation, and it's super tiny, but it means black holes can slowly evaporate over time. Yeah, even the darkest things in the universe can fade away eventually. Now, what if a star isn't quite massive enough to become a black hole? Well, if it's still pretty massive, it might become a neutron star instead. Neutron stars are wild. When a star explodes in a supernova, the core that's left gets crushed into a ball of neutrons. Imagine something heavier than the Sun packed into a sphere about the size of a city. A teaspoon of neutron star material would weigh as much as a mountain. That's how dense they are, and if that wasn't crazy enough, some neutron stars spin super fast and shoot out beams of radiation from their magnetic poles. We call those pulsars, and when their beams sweep past Earth, we detect regular pulses like a cosmic lighthouse. These things are so precise that we can use them as clocks in space. And then there are magnetars, which have magnetic fields trillions of times stronger than Earth's. They're basically cosmic horror stories wrapped in science. Alright, now back to the big picture, cosmology again. So we talked about the Big Bang and how the universe has been expanding ever since. But here's the thing, when we look at the stuff we can actually see in the universe, stars, planets, galaxies, it only makes up about 5% of everything. The rest? That's where dark matter and dark energy come in. Let's start with dark matter. It's called dark because we can't see it. It doesn't emit or absorb light, but we know it's there. How? Well, galaxies spin too fast. If only the visible matter was holding them together, they'd fly apart. Something unseen must be providing extra gravity to hold them in place. That's dark matter. Dark matter doesn't clump like normal matter. It doesn't interact with light or with us. But it still has mass, and mass means gravity. So it shapes how galaxies form and move. We've even mapped it out using gravitational lensing, where massive objects bend the light from things behind them like a cosmic magnifying glass. Dark matter shows up as invisible scaffolding, guiding the structure of the cosmos. Now, dark energy, that's even weirder. Back in the day, scientists thought the universe's expansion would slow down over time, maybe even reverse. But then we discovered that not only is it expanding, it's speeding up. Something is pushing galaxies apart faster and faster. That something is what we call dark energy. We don't really know what dark energy is. It could be a property of space itself. It could be something else entirely. But whatever it is, it makes up about 70% of the universe. So between dark energy and dark matter, about 95% of the universe is invisible and mysterious. We're living in the shadow of the unknown. Even though that sounds spooky, it's also what makes cosmology so exciting. We're on the edge of discovering things that could change everything. New telescopes like the James Webb Space Telescope are helping us look further back in time than ever before, because looking deep into space is literally looking into the past. Light takes time to travel, so when we see distant galaxies, we're seeing them as they were billions of years ago. We're peeking into the baby pictures of the universe. Now, let's zoom in a bit and talk about stars and galaxies. Stars form in giant clouds of gas and dust. Gravity pulls the cloud together, and as it contracts, it heats up. Eventually, the core gets hot enough for nuclear fusion. Hydrogen atoms fuse to form helium, releasing energy. That energy pushes outward, balancing the force of gravity pulling inward. This balance is what keeps a star stable for most of its life. Eventually, the star runs out of hydrogen. What happens next depends on its mass. Small stars, like our Sun, swell into red giants and then shed their outer layers, leaving behind a white dwarf. Bigger stars go supernova and become neutron stars or black holes. These deaths spread heavy elements into space, elements that form planets, and eventually, life. Galaxies are massive systems of stars, gas, dust, and dark matter. They come in different shapes: spiral, elliptical, irregular. Our galaxy, the Milky Way, is a spiral and it's home to around 100 billion stars. There's a supermassive black hole at the center called Sagittarius A/*, and everything orbits around it. We're also on a collision course with the Andromeda Galaxy. It'll happen in about 4 billion years. The stars probably won't hit each other, but the galaxies will merge into a new one, sometimes called Milkometa. Galaxy clusters are groups of galaxies bound together by gravity. And even those clusters form bigger structures, walls, filaments, and voids like a cosmic web stretching across the universe. When you see simulations of this, it's like looking at neurons in a brain. The universe is vast, but it has structure. So what's the ultimate fate of the universe? That's still up for debate. If dark energy keeps accelerating expansion, we might face a big freeze. The universe keeps expanding until stars burn out, galaxies drift apart, and everything goes cold and dark. Or maybe dark energy will grow stronger over time, tearing everything apart in a big rip. There's even the idea of a big crunch where expansion reverses and everything collapses back in. Right now, the big freeze seems most likely, but even in the face of these massive ideas, what's most beautiful about astrophysics and cosmology is that it connects us to the universe. We're not just observers, we're participants. We're made of the same stuff as stars, following the same physical laws, affected by the same cosmic forces. When we study space, we're studying ourselves in a way. Astrophysics helps us understand the life cycle of stars, the behavior of light, the role of gravity. It explains things like eclipses, tides, and the auroras. Cosmology zooms out and shows us the big picture, the origin, evolution, and fate of the universe. Together, they help answer questions both scientific and philosophical. Why is there something instead of nothing? How did structure form from chaos? Is there other life out there? What is our place in this vast cosmos? We might not have all the answers yet. But every telescope we build, every simulation we run, every equation we solve brings us a little closer. And maybe that's the point. Not just to know everything, but to keep asking, keep exploring, and keep looking up, because somewhere out there, in the silence of space, the universe is still unfolding and it's waiting for us to understand it.